Chapter 1, Circuit Variables and Elements. There are three variables, current, voltage, and power, and there are two elements, resistors and sources, for the first four chapters. So our variables are current, voltage, and power. The elements are resistors, and power supplies. There are two classes of power supplies, independent or dependent sources, and there are two types of each of those, voltage or current sources. The type of circuit will dictate the method of approach in solving for either the current or voltage. It depends on two factors. One, it depends on the type of elements. So if we have resistors and time independent sources, then we can use linear. These are linear circuits, which implies that we can use linear equations to solve them. If we have time-dependent elements, like capacitors, inductors, and time dependent sources, then these are non-linear circuits, which then implies that we must use differential equations to solve these. The other factor is the geometric structure. The geometric structure tells us quite a bit, because if the circuit is either in parallel and or series, then what we do here is we use reduction methods. But many circuits are neither parallel or series. That implies that we can't use reduction. So we have to use powerful theorems to guide us in the process. So that's a very brief overview. Let's now move on to focusing on circuit variables. We said that there were three variables: current, voltage, and power. So let's get some details about these variables, and then we'll start with current first. So a irreducible element has variables of current through and voltage across the element. So if we were to just draw this, we have two terminal points, A and B, or nodes, and then we have the element itself. So this element has to have a voltage across it in order for current to flow through it. So the SI units either are, we could have a unit of current is amp, a unit of voltage is volts, and a unit of power is watts. But most circuits are in kiloohm units. And as a result of this, the unit of current is milliamp, the unit of voltage is still volt, and the unit of power is in milliwatts. So you have to worry about putting in those milli because of that. Okay, like I said, the variables are current, voltage, and power. In this lecture, we're going to focus on current. That's the first variable that we're going to look at. As we know, copper is widely used in circuits. Because it's a good conductor. It's not the best conductor, but it's a good conductor. And by looking at its atomic structure, it shows why. It shows why. So what do we know? Copper atoms have 29 electrons in 4 shells. So if I take the semi-classical model of Bohr, then here's what we find. We find that we're going to have 1, 2, 3, 4. So here's the 4 shells. And then down here, I have a nucleus. And what we know about the nucleus is that because it has 29 electrons, it has to have 29 protons in the nucleus. Now, how the electrons arrange themselves, turns out that the first shell can have 2, the second can have 8, the third has 18, and then the fourth has 1 electron. So in other words, if we start counting these electrons, what we're seeing here is that there's an isolated electron on this shell right here. So when we say these shells, we really mean that they're energy levels, right? So these are the energy levels of the electrons. So now we then ask the question, why is copper a good conductor? It turns out that it's actually a fairly long answer, but to really answer this quickly, we could say that the short answer is charge screening. So if we use classical Gaussian thinking of enclosed charge, we can, so if I now paste this guy back in here, okay, let's say that this is what we're here. So if I now take my Gaussian and I enclose the nucleus plus the 3 shells, here's our Gaussian. What we're seeing here is that Q enclosed in this situation is really what? It's the 29 protons. That's why we're getting, right? So these guys have, these are the protons in the nucleus. And then the first 3 shells don't have 29, they have 28 electrons. And then these guys right here are the inner electrons. As a consequence, what you're finding here is that the net enclosed charge is then 1 positive charge. So in essence, this is what we would call Q enclosed, which then becomes Q effective, not the way you spell effective, that shows that the 4th electron shell only sees 1 nuclear charge. Let's say that in writing. So what we're saying here is that the 29th electron in the 4th shell only sees an effective nuclear charge of 1 proton charge. This charge screening drastically reduces the electrical attraction between them. I call these electrons weakly bound. Other people call them differently, depending on which topic you're dealing with. Some people call them valence electrons. Some people call them conduction electrons. There's lots of names. As a consequence, this weakly bound electron easily moves at room temperature between one copper atom to another. And to show you, I mean, this is a rough explanation. I mean, we didn't talk about the band gap and how copper really sets it up so that electrons can move easily from one copper atom to the other, but this is a rough explanation. Okay, so now that we know that the only electrons that can move are the weakly bound electrons, and of course the protons inside the nucleus cannot because of the strong nuclear force, we only talk about weakly bound electrons. Now, suppose we have a piece of copper wire. How do the weakly bound electrons move? In physics, it's common to speak in the language of electric fields. That's not true in circuits. So in circuits, it is more beneficial to speak in the language of potential fields. It's easy. That's why. It's much, much easier. Furthermore, that's what we solve for. So current in wires are a superposition of two motions. One motion, this is when the voltage is zero, or we could say that the electric field in the wires is zero. This gives us thermal motions of these weakly bound electrons in the copper. So if no voltage is across a wire, weakly bound electrons, and from now, I'm going to stop saying weakly bound, and I'm going to just say electrons, because those weakly bound electrons are the only can move. So in other words, electrons have thermal motions that lead to random with no net displacements. On average, these random walks end up at the exact same spot. In order to have motions, the voltage cannot be zero. Now we call this drift motion. So then, here we go. So a voltage across a wire causes a sluggish drift. From high to low potential. So then if we talk about current, current is a superposition of these two motions. So in other words, if we say current, we mean that current is a combination of this random thermal motion plus this electron drift. That's what we mean by current. So the basis of current then has to do with that electron drift. So the direction let's not say direction. I should say, unfortunately, there are two interpretations of current. So one of these is called electronic flow. Electronic current. And electronic current here, that means that this is the motion of negative charges. And of course, in this case, we're talking about the negative electrons. But there's a more technical flow, and this is called positive hole current. And positive current, hole current, this guy is about positive charges. And so if you were to think protons for a brief moment, protons are stuck in the nucleus and can't move. So these positive charges are not real positive charges. Therefore, the hole. Unfortunately, This is the conventional current flow. And it's the conventional current flow that's the standard in all circuit problems. So the conventional current is the standard in circuits which is what we use in this course. That's our choice. So now let's define current. So our definition of current says that current is equal to the number of positive charges that passes through some cross-sectional area in some amount of time. So mathematically, we write this as I of t is then going to be dq dt. This is our definition of current right here. And we've already talked about the units being amps, so we'll stick to that. 1 amp is about 10 to the 25 electrons passing through some cross-sectional. But this is something that you've already discussed in your Physics 4B class. Now let's go to the next thing. We want to talk about the sign convention of current direction. Signs can get really tricky, so you got to master the signs. So the sign convention for current depends which terminal, that is plus or minus terminal, which terminal the current enters. So it goes something like this. So if I have an element, let's say that this is my element right here. And I have two terminals right here. So the way current flows is we need some type of potential difference. So we're going to say that this is positive, this is negative. In other words, this is our high potential, this is our low potential. So let me copy this since I'm going to need this again. So if I have current entering right here, so current in this case, you could see here that positive current enters the positive terminal. That implies then that the current I is positive and carries a plus sign. So you got to give it a positive sign. Now, on the other hand, what if I have this situation? In this situation, what you're going to see here is that now the current is entering the negative terminal. Then we say that the negative current enters the negative terminal. So then that tells us here that the current is now negative and carries a negative sign. So now we got the sign convention here. We can then do the following thing here. One can rearrange the current equation to determine how much charge has passed through. So if I look at this thing, I could have that I of t, which is dq dt. If I rearrange this thing, I could then say that I'm going to have q of t is then going to be how much charge was initially there plus how much charge is going to pass through between a time element of a time of t1 all the way to t. But if we rearrange this just a tiny bit, we could then see that q of t minus q of t1, well, this is just an integral. And this integral then is the area, and this represents the total charge. So this equation effectively gives us what the total charge is that's going to pass over this time interval. So let's look at some examples to give you a sense of what I'm talking about. So if I think about this example, so if I have, let's say, a constant DC current, what would we expect to have? Well, if I look at this thing, I'm going to have a plot that's going to look something like this. So if this is T1, and let's say I go all the way to T, and this is I of T, and because this is DC, that means that this current, when it's on, has to be a constant. So then it turns on at T1, and then it turns off at T. So when I look at this, This here is the area, but this area has to be the total amount of charge that passed through. And mathematically, we can see here is that if I look at this charge here, this has to equal our integral of some constant dt, which means it has to be proportional to t. Actually, I'm going to run out of space, so let me move this. So this tells me then that if I now plot the amount of charge that passed through, this would then be q of t, and you could see that this t has to be proportional to t here, so it's going to be linear. So then this linear current here, let me be careful, that's not the way it should have looked. I still need T1, and I still need, let's say that this is T here. So then I'm seeing here is that there's going to be a linear flow of charge. So physically, this makes sense here, right? This makes sense since a DC circuit flows in one direction and constantly increases the charge passing through. On the other hand, we could have a second type, and we could talk about a changing AC current. So in this situation, what would we see here? So this current should be equal to, let's say, with an amplitude of 1, could be sinusoidal. So if I'm looking at this thing, maybe it doesn't turn out to T1, and then it moves up, and then it moves back down. So if I look at this, maybe I call this T1, and I'm going to call this time T. So when you look at these areas, you could see the first half is positive, the second half is negative. So there's as much positive as there is negative, so mathematically, we would expect that then Q total should be 0, and if you integrate this guy over one cycle, that will be 0. So then, of course, if we look at how current is passing through, that amount of current over a period then says that it's going to be somewhat what? How would we say this? All we know is that eventually, on average, this current should be 0, right? Q total on average should be 0 for our time. So, and again, physically that makes sense. Since because a light bulb filament has current moving one way and 1/60th of a second later, it moves the reverse direction. Therefore, there is no net charge transfer.